Hello everyone, my name is Mihaela Ștefan. I am a professional services engineer at Infinet Wireless. Thank you very much for taking the time to join our webinar. Today we are going to introduce OSPF, an important routing protocol, and we are going to see how it can be implemented using the Infinet Wireless units. OSPF, or Open Shortest Path First, is a dynamic routing protocol based on the link state tracking technology and uses Dijkstra's algorithm to find the shortest path. OSPF is described in RFC 2328 and it is an open protocol. The OSPF protocol is supported only by the InfLink 2x2 and InfIMAN 2x2 families of devices. As you can see, the standard definition introduces many new terms that you will be able to better understand at the end of this webinar. Besides being an open protocol, OSPF comes along with several strong benefits. First, there is no network size limit when using OSPF. It can accommodate any number of devices and any type of connectivity with the possibility to organize the network using OSPF areas. The convergence period is short. It takes only a couple of seconds, so it is a very efficient routing protocol. OSPF uses authentication, so you can strengthen your security. Next, the link state updates are sent only when changes are detected in order to significantly reduce the load of the network. A specific feature is that each node builds a network map describing the full topology, and then each router calculates the best path to reach every destination. Another benefit is that load balancing can be used in the presence of multiple routes of equal cost to a single destination node. Let's now introduce the autonomous system concept. An autonomous system is a group of routers that have a unified routing policy to the internet. OSPF can be configured inside such an autonomous system. Generally speaking, you need to know that the part of the network where we configure OSPF is a single autonomous system, and the other segments of the network attached to it are seen as external networks, whether they are called Internet or LAN or other type of connections. The system within which OSPF operates can be divided into several OSPF areas. The division into areas allows you to structure the network and to reduce the amount of service information. The areas have the following characteristics. Each area has a 32-bit identifier that is recorded in the IP address format. You can see 3 examples of valid area identifiers that look just like an IP address. The identifier 0.0.0.0 is assigned to a so-called backbone area. The backbone area is mandatory for the OSPF proper operation, and all OSPF areas must be connected to this backbone area. A router device, however, can be connected to several OSPF areas. Each area has its own link state database, and link state updates are sent internally. Routing information can be exchanged between 2 areas, but only through the backbone area, so you can understand the importance of having the backbone area present. In this picture, you can see an example of OSPF areas allocation. Area 0 is the backbone area, and to it we can see attached the other 2 areas, Area 2 and Area 7. Router R2 is the border router and it is included in all the areas. Next, let's check on improper area allocation. As you can see, Area 0, which is the backbone, is not connected to Area 7, so this will cause an improper functioning for OSPF. This kind of setup must be avoided. Let's now review the router classification in OSPF. Based on the network topology, we can define the following types of routers. Internal router, for which all its interfaces belong to the same OSPF area. Only R2 and R4 are internal routers in this picture, as the other devices are at the border of different OSPF areas. Next, we have the backbone router, for which at least one of its interfaces belongs to the backbone area. In our picture, we have 3 backbone routers, R1, R2, and R3, as they have interfaces in the backbone area. Next, area border routers have interfaces belonging to different OSPF areas. Only router R3 is an area border router in our setup, since it has one interface in area 0 and one interface in area 2. And last, we have the autonomous system border routers, which have interfaces belonging to different autonomous systems, like, for example, router R1 in our picture. Another important concept in OSPF is the router identifier, which is a 32-bit number and looks like an IP address. Each router in the network must have a unique router identifier, otherwise there will be inconsistencies. If it is not manually configured, the router ID will be automatically selected as the highest IP address of the loopback interfaces, if those exist. Otherwise, it will be set as the highest IP address of a non-loopback interface. It is advisable, however, to control the router ID configuration in order to avoid having duplicates in your network. Therefore, you can manually set the router ID by configuring an additional IP address on a loopback interface and setting it manually as the router identifier. Let's now review the OSPF operational principles. First, the OSPF protocol is launched in order to initiate all the other subsequent processes. The first step is to establish neighboring relations between adjacent routers, more precisely to get to know the neighboring routers. Next, the designated router and backup designated router roles are established. This is useful for multi-access networks in order to reduce the network load by sending less service packets. Once the neighboring relations are established, each router will send a link state advertisements to all its neighbors. As a result, all routers should create an identical link state database, which will describe the topology of the entire network. Next, the routers build the shortest path tree using the database and the Dijkstra's algorithm. Each router performs its own calculations in order to find the best path to reach every network destination. As a result, the routing table is populated with the routes toward all network destinations, and the device will next export the routes to the forwarding information base, or shortly the FIB. The FIB is used by the device to choose the interface that a given packet will use for egress. At this point, the OSPF convergence state is reached, and OSPF will monitor the network status from now on. When there are changes in the network, the routers send out link state updates. Afterwards, the LSDB is updated, and the algorithm is restarted in order to recalculate the best path for each destination. Convergence is reached very fast in just a couple of seconds. So this is the overall OSPF process. We introduced many new concepts, but do not worry if this information seems overwhelming, because we will clarify things shortly. Let's now discuss in more detail the OSPF processes that we introduced. First of all, in order to exchange network topology information, the routers must establish neighboring relations. The following principles apply when establishing the neighboring relations. The routers must have the adjacent interfaces in the same OSPF areas. Hello messages are exchanged using the multicast address 224.0.0.5. The OSPF timers and MTU settings on the interfaces must match on both ends. The authentication data configuration should also match on the devices. OSPF must be enabled on both sides of the link, so both devices must be running OSPF. And very important, the router identifiers must be unique. If there are duplicates, the neighboring relations are not established properly. In broadcast networks with multiple access, like the one in the picture, the designated router and backup designated router interface roles are elected in order to reduce the traffic load caused by the large number of link state advertisements. The DR will practically centralize the OSPF message transmission for this segment. Two types of neighboring relations can be established: a full relation between any router and the DR and BDR, a two-way relation between non-DR and non-BDR. Let's take router R1 as example. As you can see, it established a two-way relation with router R2, meaning that it will establish neighboring relations, but it will not exchange routing updates with router R2. Router R2 will receive the routes of R1 from the DR, not from R1, in order to reduce the load of the network. Next, we can see that R1 established full neighboring relations with the DR or R4 and with the BDR or R3. Non-DR and non-BDR routers like R1 will only exchange routing updates with the DR and BDR instead of sending the link state updates to all the other routers in the multiple access network segment. This reduces the load of the network and it is very useful. The DR and BDR election is based on the following rules. The interface priority sent in the hello packets is checked and the router with the highest priority wins the election. However, if the priorities are equal, the highest router ID will win the election. Keep in mind that the role is assigned to an interface, not to the router itself, because a router might be connected to several multiple access network segments. In such cases, DR and BDR elections will take place for each multiple access network segment, and this can cause a router to have two different DR or BDR interfaces, one for each segment. We have now arrived to the link state database synchronization process, which helps the routers to create the network topology. We will discuss the initial link state database synchronization. First, the routers exchange database descriptor packages in order to send the content of their own link state database. We can see that router R1 informs that it knows the 10.10.10.0 and 192.168.0.0 networks, while R2 tells about network 10.10.10.0. Next, since router R2 doesn't have any information about 192.168.0.0, it will send a link state request to router R1 asking for more details about it. Router R1 will respond with a link state update containing the link state advertisement about the network 192.168.0.0, saying that this network is directly connected to it. And finally, router R2 sends a link state acknowledgement saying that the update was accepted. Let's now discuss the link state advertisement types, as these messages are essential for building the link state database. LSAs contain detailed information about the network topology, and more LSAs are usually grouped to form a link state update message. The received LSAs are all stored in the link state database. The first type of LSA is the router LSA. All routers are responsible for generating this type of LSA for each area they belong to. Using LSA type 1, the router informs about its own interfaces, but also about its neighbors. Next, the network LSAs or type 2 LSAs are sent only by the designated router in multi-access networks and contains all networks and routers that are connected to this particular network segment. The summary LSAs are generated by area border routers. This way, a router located at the border of two different OSPF areas will summarize the information learned from one area and send it to the other area. Type 4 LSA is sent by area border routers as well and tells all the other routers how to reach the ASBR router, the router that is connected to the external network. The external LSAs are generated by ASBR routers and contain routes that are external to the autonomous system where OSPF is defined. The other types of link state advertisements are used for special OSPF scenarios, and we will not concentrate on them during this webinar. We use this setup in order to understand how the different LSA types propagate through the network. As you can see, we have multiple OSPF areas and couple of multi-access segments so that we can define different router roles. For example, routers R3 and R4 are area border routers, as they have interfaces belonging to different areas, while router R5 is an ASBR. As you can see, it is connected to an external domain. I want to mention also that router R2 is BDR for the multi-access segment with R1 and DR for the multiple access segment with R3 and R4. As we discussed, the DR and BDR are elected for each multi-access segment, and the router can have different roles assigned to its interfaces, like is the case of R2. In the first picture, you can see that LSA type 1 is sent by every router, no matter its role, to every neighbor in order to inform about its networks and neighbors. It is important to know that LSA type 1 is only sent internally to an area. It doesn't leave the area. Next, LSA type 2 is only sent by the designated routers towards its particular multi-access network segment in order to inform about all the connected networks. Router R2, for example, will be the sender of LSA type 2 for R3 and R4, but it will be the receiver of LSA type 2 coming from R1 on the other multiple access segment. We have come to LSA type 3, which is generated by area border routers only. As you can see, only R3 and R4 send this type of message. This way, R3 can summarize the networks of area 36 and send them towards area 0, but it will also summarize the networks of area 0 and send them to area 36 so that all routers can learn the whole network topology. Next, LSA type 4 is generated by area border routers and informs the other routers how to reach the ASBR. In our case, routers R3 and R4, which are at the border of different areas, will send LSA type 4, informing the other routers how to reach R5, which is the ASBR. LSA type 5 is generated by the ASBR and informs about the external networks. What you need to keep in mind is that initially LSAs are exchanged until the databases of all the routers are synchronized and contain the same information. Afterwards, after the initial synchronization, LSAs will only be sent in case of changes or timers expired. This will eventually decrease the load of the network. After we have a complete database, every router has to calculate the best path to reach every destination node. For this, OSPF will add the cost values for each interface along the path towards the destination. But first, OSPF must know the cost of each interface, and for this, it uses a simple formula, the reference bandwidth divided by the interface bandwidth. Since the default reference value in OSPF is 100 megabits per second, let's see what costs will result for each interface in this picture. First, between R1 and R2, we divide the reference bandwidth of 100 megabits per second to the interface bandwidth of 10 megabits per second, and we obtain a cost equal to 10. Next, between R2 and R3, we have a 100 megabits per second connection, so the default OSPF cost will be 1. And moving forward, between R3 and R4, we have 1 gigabit link speed. The default OSPF cost will also be 1, as it cannot use a value of 0.1, which results upon division. Actually, for any speed higher than 100 megabits per second, the default OSPF cost will be 1. This is a problem because it does not distinguish the speed of the links, so it cannot accurately calculate the best path. The solution, as you might guess, is to reconfigure the default reference bandwidth to a higher value. It is better to configure it to the highest interface bandwidth that you have in your network. Let's now move towards the practical part of this webinar. The OSPF configuration is performed from dedicated command shell modes. The entry point is the OSPF mode, where you can issue some basic commands like showing the OSPF configuration, the link state database, and the neighboring relations. The commands to enter a specific mode are indicated on the arrows in the picture. If you type, for example, configure, you will enter the OSPF config mode, and afterwards, if you type router, you will enter into OSPF config router mode. Each mode allows specific OSPF configurations that we will review shortly when configuring the devices. We will use this setup in order to learn how to configure OSPF on the Infinet units. As you can see, we have a multiple access topology with CPE2 and CPE3 that are in the same area and share the same network with the base station. Therefore, we expect that OSPF will elect designated and backup designated router roles for this segment. We also have to manually configure the router IDs by assigning IPs to the loopback interfaces, so we can avoid having duplicates in our network. And I also want to mention that we have two different OSPF areas, so OSPF will maintain separately databases for each area, as we will shortly see. Let's now configure our OSPF on our units, and we will find out more details. Okay, I have pre-configured CPE2 and CPE3 since their configuration is similar. So I will just show you the configuration of CPE1 and the configuration of the base station, and then we will see how OSPF converged. Okay, let's log into CPE1. I have now a default configuration on the unit. It just has a radio link established with the base station, and I will show you from scratch how to configure OSPF. As you know, we want to use the unit in routing mode, so all I want to do from the web interface is to disable switching and to remove management through SVI, okay? So disable switching and apply. That's all that I want to do on the web interface. All routing configurations are performed from CLI. So I'm going to log in to the unit using telnet. Let me show you the configuration so you can see the IPs. Okay, so we are now configuring this CPE. The first step is to configure the IP addresses on the interfaces, because in order to use the units in routing mode, we have to assign IPs to each interface, to RF and to Ethernet. As you know, when we use them in Mint with switching, we do not need to assign IP addresses for the data traffic. We only assign IP addresses for management. In this case, we assign IP addresses for data traffic. So I begin with the Ethernet interface. Okay, this is the IP address that I want to configure. Next, I have to delete the default IP address that I have on this unit. So I say if config Ethernet 0 delete. This command will delete the first IP address that was configured on the unit. At this moment, I need to change my IP address because I use an IP address from a different class. Okay. And I reconnect to the unit using the new IP address of the Ethernet interface, okay? Okay. Now we go on with the interface configuration. We have to now assign the RF interface an IP address. We will assign this address over here. This is for the Ethernet, for the RF interface. Now I want to configure the router identifier, okay? So we need to, as we learned, we need to first assign an IP address on the loopback interface. So I will assign an IP address, if config loopback interface. Okay, I will now show you that this IP address that I input is the router ID of CPE1. Okay, we want to control the configuration. Okay, now I can save the configuration and I will show you that we have IPs assigned. We have manually assigned an IP address on the loopback interface so we can control the election of the router IDs. Then we have the Ethernet interface with the new IP address and the RF interface with the IP address that we assigned. I want to show you the content of the routing table. As you can see, CPE1 only knows about its connected networks, okay? So it knows about the LAN network, okay? And the network on the wireless interface. About this network, the LAN network, and the network on the wireless interface. Next, I am going to configure OSPF so that it will be able to learn all the networks that are present in this picture and that it will be able to communicate with all the other PCs. So the first thing is to start OSPF. Then we have to enter the special command shell mode configuration. Okay. Here, if you type a question mark, you will see all the commands available in the specific mode. At this point, I want to enter the config router mode because I want to manually configure the router ID. Okay, and one more thing we have to do, and then the configuration is over. We have to advertise all the networks that take part into OSPF, okay? Let me reconnect to the unit because it looks a bit strange. I don't know what happened with the console. Okay, let me check the configuration. Okay, we have OSPF started and we have the router ID configured. We go on with the network advertisement, okay? So I enter OSPF, I enter config mode, I enter config router mode, and now I advertise the networks that take part into OSPF. I have to also specify the area, which is area 0. This is part of area 0. Okay. And network. Okay, also in area 0. This is the network on the RF interface. We have finished the OSPF configuration. So now we have to save it. In order to save it, you have to exit the OSPF command shell mode because you cannot save anything from this shell. So Control-C, then exit, configuration save, and now we enter again OSPF. And here, with the question mark, we see that we have the show command available. I will just use show neighbor, for example, at this point. You can see that it established a neighboring relation with neighbor ID 192.168.0.2, which is CPE2. So this is the router ID of CPE2. It did not establish any neighboring relations with CPE3 because it is in a different area. And as we learned, neighboring relations are established only if the routers are in the same area. So it is okay that CPE1 established a neighboring relation only with CPE2. After we configure the base station, it will also establish a neighboring relation with the base station. Okay, I will now show you the configuration of the base station, and afterwards we will see more details in the routing table in the OSPF database. Just one moment until I switch to the base station, please. I have the base station in the default configuration, so I'm going to connect to it using the default IP address. I'm changing my IP address network class. Okay. Okay, so we are now connecting to the base station. The base station is also in the default configuration, and we are going to do the same thing. We are going to remove SVI management and to disable switching, apply. And then we continue with the configuration from the command line, okay? Okay. We are now connected on the base station. Let me show you again the topology so you can see the IP addresses. Okay, so for the base station, we have a bit more to configure. The base station is area border router in our case because it has interfaces belonging to two areas. It has an interface to area 0 and an interface to area 1. So we are going to configure more networks. What is important is that this LAN network that is connected to the base station is not part of OSPF. It is an external network to OSPF, and we are going to distribute it internally to OSPF because OSPF needs to learn about it. Let's begin the configuration. The first step is the same, to assign IP addresses to the interfaces. This time we have to assign two different IP addresses on the RF interface because we have one network towards area 0 and one network towards area 1. I begin with the Ethernet interface. Okay. Then I delete the default IP address. Then I have to change my IP. Okay, and I reconnect to the unit using the new IP address that we configured. Okay. We are now on the base station. We continue with the assignment of the IP addresses on the RF interface. Okay, this is the IP address for the other area. And now we have to add an IP address for the loopback interface as well. And now we save the configuration. Now we check the routing table. We can see that the base station only knows about the directly connected networks, okay, the local area network, and the networks on the radio, okay. We now have to configure OSPF so that the base station will be able to learn about all these networks, about the networks that are directly connected to the PCs behind the CPEs. So after we configure OSPF, the base station has to learn this network, and this network. Okay. So OSPF start. What you have to know is that once we start the OSPF, it will begin to establish neighboring relations. So if everything is okay configured in the background, OSPF already is trying to establish neighboring connections. Okay. But then I enter the OSPF configuration shell. Here I enter to the router mode, and I am trying to configure the router ID first. Before we distribute the networks present in OSPF, let's distribute the external network. In order to send the information about an external network that is attached to OSPF inside OSPF, we have to issue the command redistribute connected. Okay, so this command is used to distribute the 10.10.10.0 network that is not part of OSPF inside OSPF. Okay. Next, I want to configure the networks that are part of OSPF, and in the case of the base station, we talk about the two networks that are assigned on the radio interfaces. So network 172.16.0.0/29 area 0, okay, for this part of the network. And next, network 172.16.1.0/1029, okay, but this time area 1. So it is very important to perform a correct configuration, because otherwise the routes will not be learned correctly, okay. So after this, we finished the configuration of OSPF. As you can see, the configuration is not very long, but you must pay attention to the IPs that you configure and to the networks that you advertise to OSPF, okay? Then we have to save the configuration, so I exit, go save. And now I want to check the routing table to see if the base station actually learned this time the networks that are connected to the PCs behind the CPEs. As you can see, we did a good job. We have here all the 3 networks behind the CPEs learned by the base station. So they are present in the routing table of the base station. This means that OSPF reached convergence, okay, very fast, and it populated the routing table with the correct information. As you can see, here we have information about how to reach the network behind CPE 1. We have to use the gateway, which is the IP address of the RF interface on CPE 1, okay? For reaching CPE 3, for example, we need to use the gateway, which is the the IP address on the RF interface of CPE 3. Okay, next let's check the internal OSPF configuration settings and what actually did OSPF learn. So I enter OSPF mode. Here we use show, okay? First, show neighbors. We can see that the base station knows about all the neighbors in the network, okay? So it knows about CPE 1, about CPE 2, and about CPE 3. We can see that for this part of the network, okay, for this part of the network, for area 0, which is a multi-access segment, the backup designated router is CPE 1, okay, and the DR router is CPE 2. Okay, since we have a higher router ID configured on the base station, it means that this CPE had a higher priority in the hello packets when it established the neighboring connections, okay? We have full neighboring relations established over here. Next, I want to show you the database content. So this is the database, the link state database that we have been talking about in the theory. And the link state database stores all the LSAs, the link state advertisements, that were received by this unit, okay? So the LSAs are centralized and stored here on the base station per area, okay? So for example, first of all, for area 0, we have router link state updates, which tells us actually what are the routers that are present in this area. So let's check if it's correct. It says that it has CPE 1, CPE 2, and the base station. Area 0, okay? CPE 1, CPE 2, and the base station. So everything is correct. Next, we have the network link state advertisements for area 0, okay, which tells us the routes that are learned in this part of the network segment on the wireless interface. And next, another type of link state advertisements for area 0, the summary link LSAs. So summary LSAs. As we know, summary LSAs are sent by area border routers. So we expect here to see all the other networks that are present in the other area. So we have to see the networks from area 1. So let's check on the picture. Area 1 is here. It has 10.10.13.0, okay, the first entry. And it has 172.16.1.0, the second entry. So it's correct. the base station learned for area 0, which are the networks that are present in the other area, okay? You have to know that all this information will also be propagated to the other routers. So it doesn't matter that we check the base station. The CPEs will also have this information per area, okay? They will see what routes, what networks are present in every area separately, okay? And the same is valid for area 1, okay? I will just review shortly. The router link state advertisements, which tell us the routers present in this network, which is CPE3 and the base station, that's it. The network link states, okay, or the networks that are present on the multiple access segment on the radio. And the summary link states that tells area 1 what is present in the other area, okay? So area 1 knows that in area 0 we have these networks, which is correct. Another important thing are the external link state updates, okay? These external link state updates are sent by ASBRs, in our case the base station. And as you can see, we have this network 10.10.10.0, the directly connected network of the base station, which is not part of OSPF, but it was learned by OSPF. Why? Because we configured redistribute connected, okay? So we can advertise external routes to OSPF using a command. So just to summarize, when we start the OSPF process, the routers start to exchange hello messages and they establish neighboring relations. This will be correct if all the settings match on both ends, okay? And for routers that are part of the same area. After the neighboring relations are established, only at this point we can start to exchange link state advertisements, okay? Link state advertisements will help the routers to build the database. So the next step is to build the database, okay? So after we issue the commands and we advertise the network, as you saw, the configuration is very simple. After we advertise the networks, the routers start to exchange LSAs until everybody has the same information and the same database describing the same network. The next step, which is also performed in background by OSPF, is that each router, each device will calculate the best path to reach each destination, okay? So the base station will calculate how do I reach the local area network of CPE1. And for this, it adds the cost of all interfaces until this network and builds an entry to the routing table. At the end, when all the routes are learned and exported to the routing table, the OSPF convergence is reached, and OSPF will just monitor the status of the network, okay? So we will just have link state advertisements or updates in case of changes or if any timers expire. Okay, so as you see, OSPF is very fast and very efficient. It only sends updates in case of changes, and it learns the routes very fast. Let's move on to the presentation. What I want to emphasize is that OSPF is a complex and long subject, and it cannot be taught or even learned in just one webinar. So we covered some main topics during this webinar session. However, there are still uncovered topics, out of which I want to mention a few. We didn't talk about the different area types, about the neighboring establishment process in detail, about LSA type 7, about route filtering, and about route summarization. These are the main uncovered parts, but there are still others, since OSPF is such a complex subject. In case that you have questions or suggestions, or if you want to learn more about OSPF, about the uncovered topics, please contact us at academy@infinitewireless.com. We can organize another webinar session if necessary and if we have requests on the subject. This is what I wanted to share with you today. Thank you for your attention. This brings us to the end of today's webinar. If you have any questions, please feel free to write them down and I will answer them shortly. At the moment, I see only one question from Andrew. How would you change the DR in an area? Okay, I will just move to a different slideshow. We learned in this slide that the DR is elected first of all based on the interface priority. So the router that has the highest interface priority, which we can see in the hello packets, will be the DR. If the priorities are equal, then it will check for the highest router ID. So we have only two conditions, interface priority and router ID. If you want to control the election, you have to manually assign interface priorities, okay? So OSPF allows you to configure on the interfaces many timers, priorities, and other parameters that are specific to OSPF. We didn't cover them in this webinar because it is long and difficult, and it is a new subject for everybody. So we just covered the main subjects, okay? But if you go to the interface configuration mode and you type a question mark, you will see that you have commands available to configure timers and priorities and other specific parameters for OSPF, okay? For example, you want a specific router R5, I want to be DR. You assign to it the highest priority, but then you have to go on the other routers as well and to assign lower priorities, okay? Because you want to control the process. Otherwise, you can set equal priorities because you already have different router IDs, for example, and you have to assign the router IDs in the order that you require. Okay, I see there are no more questions. Thank you once again for your time, and I hope to see you again during our next webinar. Have a nice day.